Aim 10.3 Independent and Disjoint Events. Your homework tonight is Delta Math and scrap paper is required. So let's go over some vocabulary. So, independent events. When the outcome of one event does not affect the outcome of a second event, the two events are independent. Dependent events. When the outcome of one event affects the outcome of a second event, these two events are dependent. Mutually exclusive events. When two events cannot happen at the same time, the events are exclusive events. If A and B are mutually exclusive, then the probability of both is 0. So with independent events, childbirth, selecting the gender or the sex of the child, that would be considered independent events. The fact that you had 3 boys in a row does not affect whether or not the fourth child will be a boy or a girl. Dependent events, though, will, and we'll get into that. Dependent events will affect what the outcome of a future event happening is. And mutually exclusive events, imagine that if I were to ask you, what's the probability of you being able to run a marathon in New York and simultaneously run a marathon in California? Well, that's 0 because that's impossible. So, exercise 1. Classify each of the following scenarios as having events that are dependent or independent. So, a person pulls a red marble out of a bag that has 5 blue and 7 red marbles and does not replace it. Then a person pulls another red marble. Is the probability of pulling the second red marble out dependent on pulling the first red marble? Explain. Well, the probability of pulling the second marble is dependent on the event of pulling the first red marble out. If a red is pulled first, then the probability of picking a red out second changes. Now this one, the person flips a coin and notes that it comes up as heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 dependent on having a head when flipping the coin? Well, these two events are independent. Regardless of whether a person got a head when flipping a coin, the probability of rolling a 3 is still only 1/3. Excuse me, of rolling less than a 3 is 1/3. So let's look at our second example. A spinner is spun once and its outcome is noted. Find the following probabilities. The probability of getting an even is 1/2. The probability of getting an even given that the outcome was a prime number. So now that would be 1/4. Remember, 2 is a prime number. And now C, the probability of getting an even number given that the outcome was less than 5. And that would be 1/2 also. Which event does E depend on? E being even, P being prime, or L being less than 5? How can we tell, and what is a reasonable test? Well, the event E depends on our event P. We can tell this because the fact that P occurs changes the probability of E occurring. But the fact that L does not change the probability of E, the fact that L occurs does not change the probability of E. Thus, the two events are not dependent or are independent of one another. So, conditional test for independence. If two events are independent, then the probability of A given B is still A. The fact that the probability of B is there, it has no effect on A. And also vice versa, where the probability of B given A is just the probability of B. It's as if The probability of A never existed. They exist on their own. They are not codependent. Example number 3. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below or to the side, and notice how they are sorted. They're sorted by sex and by subjects. So, does it appear, based on the data of this table, that the preference for math as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. So the probability of liking math, let's look over at math, that's 18 divided by 57. So it's approximately 32%. Now the probability of liking math given male, let's see, that's 10%, that's 10 divided by the overall number of males, which is 27. And so that's approximately 0.37 or 37%. Now the probability of math given female, we're going to look at math again, given female, 8 divided by the female population, which is 30. And that's approximately 27%. It appears that there is dependence on the gender for liking math because these two conditional probabilities are not equal to the overall probability of liking math. Notice how they affect one another. If you'll notice here, the average of 0.37 and 0.27 is the overall average of liking math. So liking math in this case, it depends on gender. Obviously, this is not overall, and because I love math, so this is empirical data analysis. So now, does it appear, based on the data in the table, that the preference for social studies as a favorite subject has dependence on a student's gender? So let's look. The probability of liking social studies is 19 out of 57. Now, liking social studies given male is 9 out of 27, or 1/3. And the probability of liking social studies given female is 10 out of 30, that's supposed to be 30. 10 out of 30, I'll make that correction on the PowerPoint, which is also 1/3. So notice here that there is no dependence on gender because the probabilities don't change at all. Now the product test for independence. If A and B are independent, then the probability of A given B is just the probability of A, as stated previously. Therefore, the probability of A is equal to the probability of A and B divided by the probability of B. If this is true, then we can actually pull both of those probabilities apart. So it's the probability of A times the probability of B. If they are independent, these two values will equal one another. The product along with the overall probability of A given B. So here's an example. There is a 34% chance that a person picked at random from an adult population is a regular smoker of cigarettes, and an 18% chance that a person picked has emphysema. If the percent of the adult population that are both regular smokers and suffer from emphysema is 14%, is being a smoker independent of having emphysema? Well, let's do the product test for independence. So the probability of being a smoker is 34%, while the probability of having emphysema is 18%. However, having the probability of being a smoker and having emphysema is 14%. So now, to check to see if these two numbers are independent, the probability of being a smoker times the probability of having emphysema must be equal to 0.14 in order to show that they are independent. That having emphysema or being a smoker has no effect on the other. However, when we calculate the product here, we get that the product is 0.0612, meaning that the probability of being a smoker and having emphysema is not independent. If these events were independent, then the product of being a smoker and the product of having emphysema would be equal to the product of being a smoker and having emphysema. Your homework tonight is delta math.